Mm. All right, so that's 10, 11, 1. Safety education.
Crazy science.
Let's do it.
So what I have is hydrogen. Crazy science.
Let's do it.
So
All right, let me go through this list here. All right, so I was able to see and hear that.
Good.
Do you plan on using breakout rooms?
No.
So I don't have a lot about you guys in the, I just have that my introduction so far is just going to be Ralph Stewart is the environmental safety manager and Megan Ferm is the senior laboratory technician in the chemistry department at Keene State College. Is there anything else you'd like me to say about you?
I think
No,
we're also introduced. Sorry, you first, Ralph.
We have an introduction slide in the slide, so that's good.
Okay, perfect. I'll make sure that I've got everything. All right, so you guys are the safety education in the 21st century.
Yep.
I'm just trying to find that. There we go. There, perfect. Well, actually, I have a little bit more.
On Ralph.
I have a little bit more on Ralph, yes. Okay. All right, looks good. All right, I'm going to mute myself for just a minute, but I'll be right back.
Sounds good.
Okay.
Hello, Alana. Hi, Kara. How are you guys? Long time no see. So we've got a couple more minutes before we start.
How's your summer been going, Georgia?
You know, it's been pretty good. It's been pretty good. It's been a very strange summer. I'm taking my youngest to college. He's gonna be a freshman. We're leaving on Friday. And I just can't believe it's already gonna be like he's gonna be in college at this time next week.
Tugging at your heartstrings, huh?
It is a little. I said goodbye. You know, my older one's gonna be a junior, so I kind of already processed that, but now it's the younger one. So it's a bit overwhelming. I mean, sort of. I mean, I'm also ready to have him go. I don't want him to go, and I'm also really ready at the same time.
Yeah, but when you get into my position, you miss them like you wouldn't believe.
Yeah. Well, I have to say, having my older son come home from college in March and having my husband working from home and me working from home since March, it's actually been really great having us all here. So I feel like I'm really going to notice the difference in September after having us all here for so long. How about you? How's your summer been going?
A lot of painting.
Like painting a house or pleasure or painting scenery?
No, house, inside cabinets that have windows, you know, that stuff. All sorts of other stuff. We haven't gone to the beach at all.
Well, you got to get that in. You don't have that much more time left before school starts.
I'm not willing to go there right now.
Oh, yeah. Yeah. It's not because you've been painting. It's because of COVID. Yeah. I
You
haven't.
think? I mean, it's a nightmare. You're down the beach, someone doesn't have a mask on, they're hawking their lungs up, and the prevailing winds are coming your way.
Yeah.
You know?
Yeah, exactly.
No, I'm not doing it. I mean, you've seen the kids at the beach. You can't corral them.
No. And teenagers have very low risk. They are high risk takers, and they're not very smart about safety.
That's because they're invincible.
Yep.
It hasn't hit them, the mortality.
Which, you know, is good.
That's one of the things I worry about with the college kids coming back.
Absolutely.
During the day on campus, they're going to follow the rules and whatnot. But at night, who knows what they're going to be doing?
Oh, you know what, Ashley? People aren't even following rules of the state. Our governor is pissed off because too many people are going to the beach and then backyard parties. I mean, survival skills are really lacking in some people. It just blows my mind.
We had, I think there was just like a week ago, there was like 34 cases of teenagers in Greenwich coming down with COVID because they had all gone to this big party.
Oh my God.
And I'm like, and I'm going to be teaching these kids in how many weeks? We'll see.
God bless you. Hey.
All right, let's wait one more minute and see if anybody else comes up, and then we'll go ahead and get started. But it's, hi Mackenzie, hi Ashley. All right, well, I'll go ahead and introduce, sometimes people wander in over a few minutes. And I need to go here. All right, so it is my pleasure to introduce Ralph Stewart, who is the Environmental Safety Manager, and Megan Ferm, who is the Senior Laboratory Technician in the Chemistry Department at Keene State College. And I know all about Keene State College because we've actually been there a few times for NEAC conferences in the past. Ralph has been working in academic environmental health and safety with a focus on lab safety since 1985 at the University of Vermont, Cornell University, and Keene State. He is currently the chair of the American Chemical Society's Committee on Chemical Safety. He has a master's degree in environmental engineering from UVM and is a certified industrial hygienist and certified chemical hygiene officer. So this session is scheduled to run from 3:15 to 4:45 p.m. And I will leave this up to you guys, Ralph and Megan. We only have, it looks like there's about 9 people here in the session. So if you want people to just ask questions as they come, you can do that. Otherwise, you can have them type it into the chat and only I will respond. Or if you want us to wait till the end, just let us know what you would like us to do.
Okay, well, that's actually sort of our first slide here.
Okay.
Is just a few guidelines for this. If you have a question that is sort of burning in, but we aren't addressing right away, put it into the chat as soon as they occur to you, because we might address that question later, or we might not, and we might want to come back to it. So a lot of times when I'm watching one of these, a question will pop up out of nowhere, and it's good just to get it recorded in the chat. So that's one good way to make this a little more interactive. We are going to do a couple of polls. We're going to use the Zoom reactions button instead of the polling feature, because the polling feature confuses me. But if you need to interrupt us at any point, just use the reactions button to put up your hand or something, rather than trying to talk over us, because it gets very confusing if there's more than one person talking at the same time. And is anybody willing to keep time here? Because I think Megan and I are going to be sort of focused on our.
I'll keep time.
Okay,
Can you explain what we do with the reactions button? I have never done that before.
So if you look at the Zoom panel, I can't see it because I'm a host, but I believe the participants should be able to have a button that says reactions. And
Yep.
if you click on that, you see either a thumbs up or a wave or something. And that's just the best way to let us know that you want to interrupt us in some way. Does that make sense?
Yes. And now
Great.
I've got a hand up in my picture, and then you take it down. Is that how it works?
I think you take it down.
I just clicked on the hand that was on my photo and it came away.
Oh, okay. All right, great.
Okay. So what we'd like to do a couple quick poll questions so that we know who's we're listening to us. So can you, with your reaction button, just tell us, do you teach biology as part of your work in high school? Does anybody teach biology? Yeah, okay, I got one person teaching biology. How about chemistry? Anybody teaching chemistry? I see several people are teaching chemistry. How about physics? Anybody teaching physics? Are the thumbs remaining up because you're teaching both?
No, it just didn't go away.
No, it just didn't go away. Okay.
But now it did.
Is there anything else that we didn't think of besides biology, chemistry, and physics that people are teaching?
Middle school general science.
Okay, another good category. So that's really our next question is, what level are you working at? So we have at least one middle school. Anybody else teaching junior high level science? How about high school level science? Yeah, we have a lot of people doing that. And how about advanced placement? So we have some advanced placement teachers as well. So yeah, okay, so as was said, I'm the chair of the American Chemical Society's Committee on Chemical Safety, and we've been reaching out to high school teachers around the country for the last probably 5 years now, trying to make sure we understand what you guys need in terms of support for safer practices in chemistry, and that we're trying to get a good sense of the demographics out there. So here's a couple more quick poll questions. What's your biggest lab safety concern? Are you most concerned about the number of students in your class, in a lab class? Lack of proper equipment, student horseplay, or something else? How about number of students in the class? I don't see anybody raising their hands on that one. How about lack of proper equipment? I see somebody reacting to that one. And student horseplay. Some people are concerned about that. Several people I see. Anything else that I should have included in those categories? Oh, spacing based, yeah. So spacing based on students, that's something that we're all facing now, is trying to figure out how to fit X number of students into a space that was not necessarily built for that. We have heard stories at the ACS about overcrowding of labs prior to COVID, and now with whatever the COVID situation is going to be, we're still figuring that out at Keene State. So we don't want to get too much into COVID with this discussion, but if people want to talk about it when we're finished with the rest of it, I can talk about what we're doing at Keene State. And I guess the last question is here: which of these have you faced in a laboratory setting? A lab fire, chemical spill, personal injury, or none of these? So how many people have had to deal with a lab fire? Okay, so it looks like we have couple of people have had to deal with lab fires. How about chemical spills? Don't see very many chemical spills here. Personal injury, somebody getting hurt in the lab. A couple of people have had that situation. So Megan, well, we'll go ahead and introduce ourselves, and we'll let Megan talk about what she does.
Hi, everybody. Thank you so much for joining us today. As was mentioned, I am the chemistry laboratory technician for the chemistry department at Keene State College. I am a former high school chemistry and physics teacher. I taught for 2 years. I currently teach undergraduate labs, depending on the need per semester, on top of my full-time lab technician position. And I'm also a current student of the safety program at Keene State College for the Safety and Occupational Health Applied Sciences program, if we're doing that in a little bit longer terms.
Okay, so my name is Ralph Stewart, and I'm a CIH, means Certified Industrial Hygienist, which is sort of a 20th century term for people who deal with environmental health and safety issues in general. And the CCHO is a Certified Chemical Hygiene Officer, which means I focused in on laboratory chemical safety. Right now, I'm doing 2 jobs at Keene State. I'm the Chemical Hygiene Officer, which focuses on the academic side of campus, and Environmental Safety Manager, which deals also with the facility side, hazardous waste, leaking ground, underground storage tanks, those kind of things. I've been here for just about 6 years, formerly at UVM and Cornell. I'm currently chair of the American Chemical Society's Committee on Chemical Safety, which is the National Committee on Chemical Safety. And I'm also active in the Division of Chemical Health and Safety for the ACS. I think this is Megan's slide.
So there are a few things we want to make sure that you are comfortable with by the end of today's session. The first one is to be able to describe and assess the risks in your labs and explain your decision-making process for safe lab practices. We would also like you to be able to use the GHS, SDSs, and RAMP. RAMP we are going to be introducing today, so if you're not familiar with that particular variety of alphabet soup, we will talk about it. We want us to be able to use them as safety tools to improve student understanding of safety expectations. And we would also like for you to be able to explain your due diligence relative to laboratory safety so that you can use them to communicate with your students, colleagues, student teachers, parents, and in the worst case scenario, the principal or the court system if something does go wrong.
We did, part of the genesis of this workshop is, people may be familiar, there was a sequence of fires in high school laboratories and other museum settings from about 2012 to 2015, and one of those was very close to ACS headquarters in Washington. And so at that point, the ACS decided we really need to get into outreach to the high school teaching community, and that's one reason due diligence is a big issue, because we are seeing in the court follow-up to those incidents a lot of confusion about what good practice is in terms of safety planning. So this is Megan's too.
Yeah, and so one of the things that we want to do first, just kind of to get ourselves oriented around what it is that we're going to be covering today, is go through an experiment that I think all of us have either done in our lives or run in our lives as teachers. And this is going to be a separations of mixtures lab. And so students are going to be given a heterogeneous mixture of sand, salt, and iron filings, which they're going to separate into components. And so part of the procedure for this is that they're first going to use a magnet to remove the iron. Then students are going to add water to the remaining salt and sand mixture, mix it up a bit, and then pour off the dissolved salt solution. Then they're going to heat the salt solution on a hot plate to drive up the water. There will be a watch glass, a ribbed watch glass on top of that to prevent splatter. And then separately, we're going to have our other evaporating dish with our wet sand heated on a Bunsen burner to drive off the residual water. And at the end, the purpose is to have students compare their percentages of their mixture with what the percentage of the larger mixture was to start.
So the question for you as a group of experienced teachers is what are the safety aspects of a fairly simple lab like this? What do you anticipate being potential sources of danger for the students as they do this work? What's the likelihood that any of those particular sources of danger will cause harm to the students? What can you do to help reduce the risks associated that you identify? And what would you need to have to be available in case of a worst case scenario situation? So does anybody want to start throwing out some ideas about what are the sources of danger associated with that process that Megan just described? Okay, so somebody mentions the hot plates as a source of burns. Bunsen burners are as well, yeah. Broken glassware as you move through, spilling the heated solutions. How about the chemicals themselves? Are there any hazards associated? Okay, hot sand, good point. Chemicals in eyes. So which of those is probably the most dangerous, most likely to cause harm to the students? Loss of attention by the students, broken glass, magnets chipping. So which is the most dangerous piece of this? So the choices I'm seeing right now are broken glass, the heat sources, and broken equipment. So let's just vote on that. So, excuse me, how many people are most concerned about broken glass when it comes to this system? I see one person voting for broken glass. How about burns, Bunsen burner, hot plate burns? See a couple, 3 people for hot plate burns. And how about broken equipment, magnets or whatever breaking down? So what we're trying to do is just sort of start analyzing any particular hazard from the point of view of whether any particular demonstration from the point of view of what the hazards are and how would you do control those hazards. So as we think about how we're going to reduce this risk and what's the worst case scenario you want to be prepared for, we also want to think about who might ask you these questions. So the way you explain it to a student may be different from the way you explain it to a parent may be different. You explain it to a student teacher may be different than the way you explain it to the principal or somebody who's looking into an investigation. So who would you think are the most important audiences for answering these questions? Students are a significant audience, yeah. Has anybody ever had an experience in trying to explain chemistry labs to a principal? Students are first, yeah. Principals only get interested if something goes wrong. That's what I've noticed from the trials and other kinds of legal activities, that the principals almost always say something like, well, we assume that the chemistry faculty were following safest practices and we don't know why anything could possibly go wrong. The nurses go in with the principals as well, yeah. So the nursing staff may or may not be ready for what comes up. And I agree there's a lot of education that principals could use in terms of overseeing the chemistry labs that their teachers are doing. Would you assign this as an experiment as a home exercise? Do you think this is a good thing for people to be doing at home? Yeah, some people possibly allow it to evaporate overnight rather than trying to burn it to boil off the water from the situation. Other people not sure that is a good thing for students to be doing at home. So the key point here is that we want people to be ready to be able to explain why things are safe enough for the work that they're being to do. And the ACS has the ramp process to help us do that. So I think I'll let Megan talk about the difference between hazard and risk.
So you've already heard us refer to these terms in this presentation, and I think that hazard versus risk is definitely a little bit more of a safety world kind of conversation. But from a conceptual standpoint, it is, I believe, extremely important. And so as we'll continue to talk about it, it is, in my opinion, definitely worth it to have a conversation about what these terms mean. And so a hazard is something that has the potential to cause harm. And we think of this as an intrinsic property, particularly of a chemical in terms of our chemistry courses. And a risk is a measure of how likely it is that damage or harm is going to be caused. And so it's a little bit of a weird concept for sure. So we're going to go through this through an example. So if you wanted to cross a street, for example, cars are going to be a hazard. It's something that is present anytime there's a road. That is the purpose of a road for cars most of the time to travel across. And so the intrinsic property, if you will, of this source of harm is the presence of our cars. Depending on what situation you're going to be in, you could either have more likelihood for a car to cause damage or less. And so if we're talking about a very busy street, you are much more likely to run into issues with moving vehicles than if you're walking across a pretty empty country road. And so again, the hazard being the cars, you're going to have a higher exposure on a busy road, so there's going to be a higher risk. And you're going to have lower exposure on a less populated road, and that's going to give you a much lower exposure. And we wanted to give everybody a little bit of an opportunity to think about what this means in terms of specific examples that you could absolutely run into in the laboratory. And so we're going to do a poll. So for this first question, we'll do these one at a time. I want you to try to determine whether these are going to be hazards or risks as we present them in this specific situation. So in preparing for an experiment, you note that the concentrated hydrochloric acid has a health rating of 3 on the NFPA scale, where 0 is the lowest and 4 is the highest. Is this considered to describe a hazard, or is this a risk?
Would you like us to maybe do the thumbs up for hazard and the hand for risk?
I'm monitoring the chat box, so that might be the easiest way for us to do that, if everybody's comfortable with that. Or let's stick with the chat box just to keep it uniform. I'm seeing everybody so far indicating this is a hazard, and that is perfect. Does anybody want to elaborate as to why that's a hazard? And if you don't, I'm happy to do it. I'm reading that it is an intrinsic source of injury. It is a property of the acid, and it's not dependent on the situation. Exactly. So this is inherent to the chemical. Awesome. You guys are killing it. All right, so the second one is students are likely to have low exposure to hydrochloric acid because they'll be working in a fume hood. Awesome. Everybody so far is doing great. It is absolutely a risk. Does anybody want to explain why? Excellent. So it looks as though everybody is bringing up excellent points. So you can control, it has to do with the control, how much you're exposed to. It is definitely very situational. The fume hood removes acid vapors. Somebody already knows about engineering controls, which is awesome. And so for this last one, hydrochloric acid is also corrosive, so students should be careful when using it. So Ashley is already jumping the gun and giving you a little bit of an explanation as to why she picked hazard. And because the acid's nature, it's an intrinsic property for that acid to be corrosive. That is an intrinsic property that can cause harm. So that is a hazard statement. There we go. Ralph, did you have anything you wanted to add to that one?
Not yet. We'll keep
Okay.
going.
Sure. And so one of the things that we want to focus on is shifting from a rule-based set of rule-based lab safety to reasoning-based lab safety. Rule-based lab safety is going to focus a lot more on those intrinsic properties, and reasoning is going to be based a lot more on your situational conditions. And so what we're going to end up seeing here is that if we are able to engage students in the process for which we are developing our rules, they're much more likely to, in my experience, listen. So for example, when I've had students who have asked, why am I wearing my safety glasses? If I tell them because it's a rule, sometimes they'll listen and sometimes they will not. And I'm sure that many of you have had similar situations. But if I'm able to explain to them that even though you're literally just working with water, the fact that we have glassware present means that if something were to fall and that glass were to shatter, your eyes would be protected if you're using your safety glasses. And so I found that by going through and recognizing those hazards and explaining them in a meaningful way is much better than just listing off a rule and saying it's the rule, so they must follow it. If you also have good reasoning for your safety practices, it's also much easier to explain to a wider audience. So again, that's including your students, of course. That's including your colleagues, your student teachers, parents when they get involved, and our worst case scenario if something goes wrong as well. And we also have the ability to reevaluate our rules based on our situation if we're using situational based reasoning for those rules.
So what we've done so far is pretty much relied on our intuitive approach to identifying hazards and risks. But as a safety professional over the years, I have been using a system, the general system for identifying and managing risks. And that sort of influences the way I approach things. So when Megan and I started talking about the separations project, she had a fairly concrete teacher-oriented approach to it, but I had more of a safety professional approach. So and this is based on all the different laboratories that I've worked with over the years, whenever I approach doing a risk assessment in a laboratory setting, I start thinking first in terms of physical hazards, such as the Bunsen burners, hot plate surfaces, hot liquids, and I think in terms of chemical hazards. So in the case of the separation project, the iron filings are a significant chemical hazard. This picture I have here came out of a newspaper from 2012 or so, where a high school teacher is throwing iron filings into a Bunsen burner to get this big flame and attract the kids' attention as to how powerful, I guess, science is. But he doesn't really, from the way the newspaper story wrote about what he was doing, he was not explaining to them any of the safety aspects of it. So even though iron filings on their face of it sound pretty innocuous, there is a significant hazard associated with iron filings if they get into the Bunsen burner. Silica, if you look at SDS safety data sheet for silica, you'll see a lot of concern about long-term chronic breathing of silica or cancer associated with silica in your lungs. Not really the situation we're facing with sand in the experiment we described, but it is a hazard we should recognize, because anytime, my experience is that anytime somebody finds out a chemical they're working with is a carcinogen, they will get very, very upset whether the cancer hazard is significant or not. So that's sort of the first step I take in terms of identifying risk, hazards and risk, is to think about physical hazards and chemical hazards. And the goal is to develop a process where you can explain why what you're doing is safe enough. And we call that document that comes out of that process a risk assessment. A risk assessment is a structured explanation, a description, maybe a paragraph, maybe 3 sentences, maybe a book, but something that's fairly well structured, that points to evidence, which is usually safety data sheet information or other procedural information, that explains why the safety management system that you're using is safe enough for the project in that location. It's specific to the location you're doing it. So if you read a demonstration in a textbook, you can't do a risk assessment until you start including the factors associated with your classroom. So I know some high school classrooms have fume hoods, other high school classrooms don't have fume hoods. So if it may change what you can do safely in that classroom, and as you write a risk assessment, you should include those factors in there. In some settings, we call those risk assessment documents safety cases. That's the words I like, because it makes the point that you're focusing on the safety of the work you're doing rather than the hazards of the work you're doing. But risk assessment is another term. So I mentioned in passing the safety data sheet. I'm hoping that most people have had some kind of training around the globally harmonized system at this point. People who work with chemicals on a routine basis, but just a quick review of what the GHS is. Starting in about 1990 at the Rio conference, Earth conference in 1990, the UN started developing a hazard classification system. At that point in 1990, there were words like toxic, flammable, and corrosive on the labels of chemicals, but there was no definition. There was no global definition for what those words meant. And there was actually a word, chemical imported from China with an English label that says hurt skin hardly. And the lab tech who found that chemical and read that label in the US said, well, it hardly hurts your skin. You don't have to worry about it. And that's not what they meant in China. It meant it really hurts your skin hard. And so there was an unfortunate situation as a result of that. So as the world economy really started to globalize in the early 90s, the UN recognized the pressure of requiring a worldwide system for describing chemical hazards. And so that's called the Globally Harmonized System for Classification and Labeling of Chemicals. And its primary goal is to, number one, describe the criteria for a hazard, and number two, communicate that hazard through a set of labels and SDSs. So I'm hoping that most of you have seen these symbols before. There are 9 different pictograms that are associated with the globally harmonized system for 9 different hazard classes they recognize. 5 of those hazard classes are physical hazards and 5 are health hazards, which adds up to 10. That's because the corrosivity hazard right here, you can see it's both for metals and for human skin. So it's both a physical hazard and a health hazard. So there are these 9 symbols that you should find on any chemical container that's older or younger than 2013. So Megan and I have found several containers in the Keene State stockroom that don't have these symbols on there. That is a incentive for us to get rid of that chemical because we know it is older than almost 10 years now, and we're not convinced that it's ever going to be used. In addition to the pictograms, there are also signal words, which are danger or warning. There are 2 signal words in the GHS system, and they tell you a relative hazard associated with that particular property of the chemical. In addition to the chemical hazards, the process hazards, or what I called in the last slide, the physical hazards, which are those things related to the equipment, the procedures, and the setting: flames, high temperature, pressure vacuum systems. So I'm used to dealing with the undergraduate and research laboratory setting in academia, and at Cornell and other places, I dealt with a lot of really exotic chemistry. In the high school setting, you probably don't deal with quite as many exotic, much chemistry, but I know there are high schools where people do fairly high-end undergraduate style research as part of their academic work. So if you get into that kind of stuff, that's where you have a lot more chemistry, chemical safety to address. So in the GHS, as I mentioned, there are different signal words: danger, warning, and there are some chemical labels that have no signal word on them. So the reason that they get these different warnings is based on the property of the chemical involved. So for example, if you're talking about a flammable liquid and the flash point is less than 73 degrees Fahrenheit, which is room temperature. So if it's likely to start a fire at room temperature, it's considered a danger chemical when it comes to flammable liquid. If the flash point is higher than 73 degrees, it's a warning chemical. So in addition to seeing what pictograms are on there, you need to look for the signal word to get some sense. Danger, in my mind, danger means that it's immediately dangerous at room temperature under normal conditions. Warning means that the chemical has to be heated or under some kind of unusual condition to be a danger. None means there's almost no condition under which you can consider it a dangerous chemical. The process of assessing process hazards, evaluating the risk of process hazards, means you're prioritizing those hazards based on the likelihood of an adverse event, the severity of the event, and considering who will suffer the consequences. So a lot of times in laboratories, we have situations where there are more than one person working on the same project. So somebody has an event. It's not just themselves that may be at risk, it may be other people as well. So that could impact how you manage the event in the safety in that situation. So we're interested in, here we have a chemical, nitric acid. Here's the molecular structure. Here's a label for nitric acid. You can see it doesn't have the GHS symbols on there. Intuitively, what hazards do you think of when you think of nitric acid? Just tell us in the chat. So some people are mentioning noxious gases, corrosivity, skin issues, reacts with bases, produces heat when added to water. Yep, those are all things that I like people to think about intuitively. But nitric acid is an interesting acid. Anybody else can think of anything associated with nitric acid? So there's the vapors, disposal issues. Yeah, that's related to what I'm thinking about. So the key element with nitric acid is, in addition to being a corrosive, which we see here with this pictogram, we see this other pictogram here, which has a flame over an O. And that means it's an oxidizer. And the oxidizing capability of nitric acid is something that creates explosions in laboratories on a fairly routine basis. About once a month, somebody will pour a little bit of nitric acid in with a waste container, which also happens to have some organic in there. They'll close the lid tightly, and then about 3 hours later, there's an explosion when that container explodes, because the nitric acid and the organics just sit there and react with each other and pressurize the container. So the oxidation, nitric acid is unusual in the fact that it's an oxidizer, even at low concentrations. A few chemicals, like a few acids, like very strong sulfuric and perchloric, are oxidizers, but nitric is something that people often don't recognize as an oxidizer. In fact, if you look at an SDS, so this one I'm showing you right now is for 9 molar nitric acid. If you reduce the concentration to 0.2 or 0.9 molar, you can see that it's downgraded from a danger chemical to a warning chemical, and all it has is an irritant with it. And if you reduce the concentration even further to less than 2.2 molar, the danger of the signal word goes to none, and there's no pictogram associated with it. So somebody mentioned earlier the idea of concentration as being core to identifying the hazards, and that's sort of how this plays out in the GHS system. You can really use the GHS system in interesting ways to sort of evaluate the risks of working with a chemical. This is Megan's, I think.
And so as we start navigating through all of these potential sources of danger to our students, what we want to do is we want to try to look at ways that we can really minimize or manage those risks. And so the most effective way to mitigate a risk is to either eliminate that chemical or to substitute it with something else. If you remove what can cause harm, then you have completely mitigated that issue. That is extremely effective. If that is not possible, and in a lot of cases, we're not able to do that in chemistry labs, that's part of teaching, of course. We can also implement engineering controls. And that is really a machine that helps you to isolate people from the hazard. And so the most common example of this that we see in our classrooms is going to be with our fume hoods. After that, administrative controls will help people change the way they work. And so that's going to be, for example, your really solid lab intros where you're making sure that students are aware of what they need to do, where all the safety equipment is. It is with proper signage to indicate where different types of chemicals are going to be disposed of. As we just discussed, you don't want to have your nitric acid mixed with your oxidizers. And really our last line of defense is your personal protective equipment. This is an extremely important piece, but it is not the most effective way in which we can prevent students or really anybody from having our labs cause harm to them. We do want to make sure that we're using all of these in order to create the safest atmosphere that we possibly can before going through and running those laboratory activities. So again, if we can, sorry?
I was just going to throw in an anecdote from Cornell about PPE. So I gave a presentation to the Cornell chemistry department about personal protective equipment, and afterwards the glass blower, they have a full-time glass blower there, came up and said, you know, the most important thing, you didn't mention the most important thing about PPE, which I learned the hard way. Never accept a piece of glassware from somebody who's wearing gloves, because a student had come down and handed him a piece of glassware wearing gloves, and as soon as he touched the glassware, his hand started to burn because there was nitric acid on the outside of the glassware, and the student was unaware of that. And that's sort of the key point about PPE. It might protect the student from a very specific hazard. It doesn't do anything for the environment around there or for the next person to handle that piece of equipment. So PPE is a pretty limited form, although it's a very common form of protection in laboratories. Sorry to interrupt.
Oh, no, you're fine. And that's not to say that students shouldn't wear eyewear because it's not effective. That's not what we're saying at all.
Yeah.
We're saying that there are other ways of reducing hazards that are more effective than strictly implementing PPE, or the proper usage of PPE.
Next slide.
And
This is your,
so the next thing I want to do is I want to share an experience that I had actually fairly recently in my job. And I'm sure it's going to be similar to things that you all have done or will continue to do as educators. I had a lab instructor, a professor actually, walk up to me and say, I'm going to use nitric acid for this experiment. What gloves do I need? So they skipped all the way down to the PPE. And I'm so happy that they were willing to reach out and get support. That's not I'm not upset about that whatsoever. But my immediate reaction to that, knowing the particular hazards that are associated with nitric acid, is, do we need that? Do we really need to be using nitric acid? I said it a little bit nicer than that. But we ended up going through and determining that based on when the lab was going to be run, elimination was not going to be, or substitution were not viable. We weren't going to be able to get anything else that we could substitute in time. And absolutely, we were able to encourage the use of proper ventilation through those fume hoods. We definitely know that we need to store any of that waste completely separately. Having secondary containment, that was also another piece that we absolutely implemented. And by the time that we got down to making sure that students were aware of what they were working with, we were able to come up with some pretty good pre-laboratory exercises for those students. And by the time we got all the way down to the very end, we had determined that the concentration of nitric acid, which the students would be using, is going to be low enough to where they could certainly just use their normal nitrile gloves. But if they were to get something on their gloves, to just change those gloves immediately and wash their hands. But to me, that's what RAMP looks like in action. And so now to kind of turn it over to you all to hear more about your experiences and to hear more of your insight. Based on the separation activity that we did earlier, what emergencies should we be prepared to address? To bounce off of the practices working with open flames, about a year ago, before everything kind of went into shutdown mode, one of our lab instructors had a student who accidentally tipped over a Bunsen burner and started burning through the hose. So that might not be something that we would have necessarily anticipated, but that is something I always anticipate now in terms of what students might be doing, for sure. And so I'm seeing a lot of burns and cuts and broken glassware. If students spill something on the floor, being able to slip. Definitely issues with working with hot equipment. Hot glassware looks exactly the same as cold glassware, so that can be very concerning at times.
So people are mentioning cuts and burns, and what that brings to mind for me is first aid kits. And I wonder how often people check their first aid kits to see, number one, are they filled, and number two, is the stuff in there, has it expired yet? Because in my experience in opening laboratory first aid kits is that tends to be a third full and most of the stuff has expired. And I'm just curious what the high school situation is.
Hopefully not my labs. Um,
Well, next door.
so what do you as educators think that you will need to have in order to be prepared for some of these issues? So we've done a lot of anticipating what could go wrong. What do you do if something goes wrong? So if a student gets a burn, for example, what should be your course of action? Awesome. I'm seeing some eye wash, safety shower. Excellent. And this is an honest question, do high school teachers have the capability of treating these things in their rooms, or do you send students to the nurse's office?
Good question, it sounds like.
I know that I've always kept Band-Aids, but I typically, okay.
I definitely think any situation like that should be reported to the nurse. But yeah, having Band-Aids and ice in the room itself for immediate first aid, I think there's a common sense approach to that. You would need to have some kind of facility available in the room.
What do you all do if you have some sort of either drill or lock in place, or sorry, shelter in place situation if you're engaging in labs? Is that something that you all consider, or? Awesome, excellent to turn off the valve for the gas. It's the quickest way to get those Bunsen burners to go out reliably, for sure. And so these are some of the things that I think that we have to think about holistically. I know that we had an incident where we were without power for a really long time at one point. And Ralph, I don't know if you want to speak to this, this at all. You know much more about the systems than I do in terms of a power outage. And these are all just very strange things that can happen that I think are really important for us to consider, because if this happens, it can absolutely impact the safety of our students, whether it's something that happens directly because of the laboratory that we're running, or if it has to do more with the lab causing harm outside of its intended parameters, I guess is the way I want to say that. So Ralph, I don't know if you want to talk about that power outage that we had.
Well, the power outage at some level was an act of God in the sense that it was a squirrel that got into the wrong place. So I did visit all the laboratories that were happening and sort of did an assessment that there was no hazardous activities going on that the power outage would affect that particular day. But if I hadn't been on campus, I'm not sure how we would have figured that out. So it is something you may want to consider for your specific. And we do have backup power at Keene State for the Science Center, but it failed that day because for reasons that were technically beyond my scope. So you want to think about what are the worst case scenarios and how your local situation you need to respond to your local situation. So we're not trying to answer everybody's question. We're just trying to give you a chance to sort of start thinking about this before you get too busy with all the activities associated with school. The American Chemical Society has, over the last 5 years, put out a lot of information about best practices for teaching laboratory chemistry safely, both at the secondary school level and at the academic level, undergraduate and graduate level, graduate school level. Both of these are available for free. Download them as PDFs from acs.org/safety. The guidelines for chemical laboratory and secondary schools is the better of the two, in my opinion, because they include a lot of basic technical information associated with I would say even the first 2 years of undergraduate chemistry. It goes into good detail about all the steps of the ramp, including GHS, signal words, process hazards, helps you identify the key elements. It won't address the research hazards, the hazards of a research laboratory very completely, but it does a good job of providing an overview of secondary and lower undergraduate level. And then this one is actually a shorter book because it's designed to be more a guide to the literature you need to use to get for the upper level research laboratories. In addition to the ACS, there are other partners that we're working with, particularly the National Science Teachers Association. And there are a variety of documents that have been released by them and us. The NSTA has a document on their website that describes the legal aspects of lab safety and education for the educators. It's written by educators for educators to address legal aspects. I sent those to the conference organizers. I sent these statements to the conference organizers this morning, so I think they should have them available for you. There is a ACS safety guidelines for demonstrations. This is designed for people who are taking demonstrations out into the community, what you should consider in terms of transporting hazardous chemicals. There's a lot of ACS work, outreach work, where chemists take experiments out or demonstrations out into the community and do demonstrations, and we provide guidelines for doing that. The top bullet item here is a pretty technical item, but it's something that the National Fire Protection Association put together. Their code number 45 is for safe lab practices. And the key point here is that based on the fires that they saw between 2010 and 2015, they wrote requirements that people who are teaching laboratories write a site-specific risk assessment to demonstrate that they've thought through the hazards of the work they're doing. The NFPA is legally binding in some locations, not in other locations, and it depends on what year your location. New Hampshire is a little bit behind in terms of adopting all the various NFPA codes. So this may or may not be legally binding in any particular jurisdiction, but it's definitely best practice. And if you, in a court case where somebody was working with a flammable liquid, it's something that would definitely be brought up as evidence of whether or not people are following good practices when the incident occurred. So the NFPA 45 is a key document. NSTA statement on safety in the media is key, and the ACS safety guidelines these are more aimed at the legal expectations for best practices when it comes to safety. So I'd like to sort of talk through the ramp rubric that we put together from the ACS for safety relative to the elephant's toothpaste demonstration. People may be familiar with the elephant's toothpaste demonstration. It's a fairly popular demonstration, particularly over the last 5 years. What you basically do is you take a beaker of hydrogen peroxide. Some people like 3%, some people like 30% hydrogen peroxide, depending on how spectacular they want it to be. They put in a little bit of soap, and then they throw in a catalyst, and foam starts coming out of the container. So in a classroom setting, this might be something you see just a kid. If they're working with 3%, it's pretty low hazard associated with the 3% hydrogen peroxide. You do have a mess to clean up when you're done. But if you watch TV, you may see something like this, where they put together different food colorings in the different containers as they erupt. And actually, one of the recent Miss Americas did the elephant's toothpaste demonstration as her talent portion of her entry and she won, I believe, the Miss America thing. And then this is a fellow who decided to do it in his backyard and managed to overwhelm his house in the process of doing elephant's toothpaste. So elephant's toothpaste is popular because it sounds, if you say, well, hydrogen peroxide turns to water, where's the hazard? It sounds pretty benign, but it can go bad. There's oxygen gas coming off, there's heat coming off. So I'd like to show you to help this lead a discussion. This is a video from a Ohio TV show where they bring in a professional demonstrator to show the elephant's toothpaste and just sort of think about the safety aspects of the work that he demonstrates.
Crazy science.
Let's do it.
So what I have is hydrogen peroxide.
Okay.
It's not the stuff you have at home. This is 35% concentration. You have 3% at home.
Okay.
More than
A bit
10
different.
times more concentrated.
Okay.
Okay. Definitely don't want to get it on our hands. That's why I have some down in this container.
All right.
Some food coloring. Probably a lifetime supply of green food coloring. Go ahead and dump
I
that.
would say it is. Okay.
We want this stuff to be very, very bright when we do it.
Yes,
Now,
sir.
the hydrogen peroxide is actually H2O2. Sounds a lot like water, right?
That it does.
Has an extra oxygen molecule. What we are going to do is we are going to release that extra oxygen atom, create a lot of oxygen gas. Now, we want to capture that in some soap. Can you just add a whole bunch, just a big
course.
squirt,
All right.
huge squirt down inside there? Perfect. That is perfect.
Okay.
I'm going to do the same with mine over here.
Should
And
I put on some gloves?
you should put on some gloves. It's going to get messy because it's super. Chemistry is really kind of cool because right now nothing is really happening that we can see. But if we add a catalyst to this, some potassium iodide, we are going to very, very quickly break down that hydrogen peroxide. We're going to get a ginormous, well, let's just do it and find out, okay? I'm not going to tell you what's
Do
going
I
to
need
happen.
to scoot back?
No, I think you'll be okay.
All right.
So we'll give you a little countdown. Just go ahead and pour that in.
All right.
So we're going to go 3, 2, 1, dump
All
that
in?
in. Yep, all at once. What that's going to do is break down the hydrogen peroxide inside there, and we're going to start to generate a lot of oxygen gas. The soap that you put inside there is going to help capture that gas.
Okay.
And it's a little cold out here today, so most chemical reactions slow down when the temperature is cold.
Very true.
But as this begins to come out, we're going to generate a ginormous bundle of foam. And
Look at that.
it kind of looks like a tube of toothpaste being squashed, and that's where the name
Yes, it does.
elephant's toothpaste comes from. Now, you had a flat, graduated cylinder there, okay? So you get this kind of stuff that comes out and flows over. We're going to see what happens if we do the same reaction. You don't want to touch it
I
because
was about to say, I really do want to touch
there's
that.
some steam coming off
I
the
do
stuff.
see that
It
as
is
well.
a exothermic
So will
reaction.
it'll burn.
It will actually be a little bit warm.
Okay.
Definitely don't want to touch it. And you might want to remove your phone from the table there. I'm going to do the
You're gonna set
same
this down?
sort of thing you did,
Okay.
but again, in the flask. So we're going to generate some pressure here.
Uh-huh.
We're going to see what happens. So I'll pour it in. And as that reaction proceeds, we're going to get
That scared me to
a
death.
nice little squirting of oxygen gas. And look at the steam coming off that. You
I
can stick
see
your hands
that.
on it. We can actually warm up out here today because it's so
You
warm.
really could.
It is
Okay, so that's
crazy science.
the video. And I'm curious what your reactions are to the safety aspects of that work. So somebody mentions that doing it outside helps, yes. But he is going for the effect. He's not really. So I was a little distressed when she wasn't wearing gloves in this opening picture. And when they point out the phone on the table, that was distressing to me as well. Because did anybody catch what concentration the hydrogen peroxide was? 35.
35%.
Yeah, 35%. That's not some. That's so 70% is self-boiling. 30% I used when I was a lab tech at Cornell, and if I made the mistake one day of opening it outside the fume hood, and I got a snootful in my eyes, and it was a bad news. So he's really using significantly concentrated hydrogen peroxide in there, and he's doing it relatively casually. The fact that he didn't have the woman put the gloves on, the fact that her phone was on the table, it's a little irksome to me that he's a professional demonstrator and doing this in this way. But as somebody mentioned, being outside, so what's the product of the degradation? there are two basic reaction products. What are they? Oxygen and water, right? So the hydrogen peroxide breaks down the oxygen and water. So the oxygen gas coming off of there outdoors is not such a fire hazard as long as there's no source of sparks around. Indoors, there are a lot of sources of sparks that you may not be aware of until the bubbles get to it. And there are some people who feel the need to go around and blow up, explode the bubble with a little match or something just to make it more spectacular. So there are a lot of, I think this guy's pretty good. I think he does a good job of pointing out different scientific observations as they go through in the minute and a half or 2 minutes with a audience. The woman there is got the attention span of a 2-year-old maybe, but it's a little difficult to keep her on task, but that's probably true in most educational settings. So what I did is the American Chemical Society, we put together last year a little rubric for going through the ramp for a demonstration or a exercise to figure out how, not whether it's safe or safe enough. There's no magic line here. It's rather if you were going to compare two different methods, like for example, using 30% hydrogen peroxide versus 3% hydrogen peroxide, what are the relative rankings of those two things? And so we included 5 elements in this rubric: the teaching points that you're making in it. So I think he does a pretty good job of pointing out a variety of teaching points: the ectothermic reaction that increases temperature, the impact of the container shape on the way the foam comes out of the package, and the environmental impact of the reaction on the environment. The temperature increase in temperature. So I do notice 2 or 3 learning points in there that are probably pretty valuable learning points. When it comes to recognizing the hazard, at least he does acknowledge that hydrogen peroxide is potentially dangerous. He doesn't really mention that the oxygen gas coming off, it could be dangerous. He does mention the heat. So he does at least mention the different hazards. He doesn't really do much in terms of assessing the risk or pointing out which are the most dangerous. He does mention the peroxide is the most dangerous of it. And he does sort of back the woman off from touching it, but that's part of the heat control. He, as somebody mentioned, by being outside, they have much more ventilation than they get inside. So that's inherent to that demonstration, to that site. He added that. Personal protective equipment was a little sloppy, letting the work go forward without the woman having gloves on. And he didn't do a great job of controlling her. She almost put her hands in the foam while it was hot. So that's a risk that I think he was sort of overlooked because he was assuming he was working with a adult. And then we don't know whether he was ready for an emergency. Nobody mentions how they cleaned up that mess, whether it was safe to be, and we don't know if he had somebody nearby that if there had a fire started from the oxygen, whether he would have had help available. Are there points in there that I didn't mention that you think are important to this? Yeah, so is this a good model for our students in terms of safety? That, to me, is the core point. So he did in my opinion, he did a good job in 2 minutes of teaching a fair amount of science. He did very little in terms of teaching safety. And that's one reason the ACS is putting a lot of resources into bringing the education out to the community in general, education community in general. So we don't think that people are familiar enough with a lot of the resources that are out there that they need to need. And this is another important point. I had a student ended up covered in hives just from using the 3% because she was allergic to it. And there are a lot of chemicals that we don't understand allergic reactions to until we start seeing it in class. And if you have a diverse population in your class, 20 students, one of them is going to be 5% of the population that might be allergic to hydrogen peroxide. So another important reason for best practices in terms of minimizing exposure. So thank you for raising that point. So this rubric from the ACS is part of the package I sent to the organizers, so it's available from that. And it just helps you step through the various parts of the RAMP process to help document what your thoughts are about the safety of what you're doing. And in my opinion, this is a good risk assessment for a teaching environment. I think is a good way to document what you're planning on doing. Megan?
And so I think the last major point we wanted to discuss today is how we can operate safely within those next generation standards. And so we know that one of the cornerstones of the NGSS is to have students engaging and to be working with a lot of those experiments. That's what makes us good. It's a scientific method and action. And I think that what can be really difficult for a lot of especially new teachers, and this is something I've experienced myself, is that it can be really intimidating to go into a classroom and start teaching science labs for the first time. I know that when I ended up actually in my first year teaching, I got an alternate certification for chemistry and physics. And so what that meant was that I had no teaching degree whatsoever. And so that, and the fact that I was teaching in a super small district that had no other chemistry or physics teacher present, meant that I was very concerned about creating and running my own labs. So that was really something that I drew from and was able to identify that this is a problem, I think, for a lot of new teachers, maybe me more so than some others. But by using that RAMP process, what we can do is hopefully to give teachers, especially new teachers, the confidence that they have gone through everything they needed to, and that they feel as though they have been able to provide a safe way for students to engage in these laboratory experiences. Another thing that's really cool about the NGSS is that they don't specifically tell you what you can and can't do in terms of specifically chemical reactions. And so if you're able to find a way to incorporate a safer alternative that has just as much educational value, it's a great way to operate. Thank you.
So as I said, the ACS is very interested in supporting teachers in teaching, in addressing the safety issues they're facing as they teach chemistry in high school. We've had a lot of questions about things like chemical labeling practices, glove selection, chemical storage, lab ventilation requirements, chemical waste disposal. There is an American Association of Chemistry Teachers where most of this information is stored. Some of the material is members only, others is free for everybody. So if you need help finding that at the AACT website, let me know. I can help you track down what we have out there. If there's we'd be very interested in developing FAQ style documents to help address these. Unfortunately, a topic like chemical waste disposal is very hard to put into an FAQ style document because the regulatory requirements for chemical waste disposal are very, very complicated. And it's hard to come up with a simple answer, even for a straightforward thing like nitric acid. There's a lot of ifs, ands, and buts associated with something like that. So if you have ideas about things that would be valuable for you in terms of safety, let us know, and we can put some of the ACS resources in that direction. So there are 3 key takeaway points we wanted to help you get from this workshop. Primarily the difference between hazard and risk as expressed in the GHS system. So we know that you're required to have the safety data sheets, you're required to have the GHS compliant labels, but there's a big difference between having those on hand and being able to use them to make practical decisions. And that's what you want to do as you build your risk assessment, is relate your decision to the information on the safety data sheet or the GHS. We wanted to provide an example of using the RAMP reasoning to identify best practices and help you document the due diligence that you do in setting up your laboratories by documenting a safety case to describe how you're going to manage risks. I think there's one more slide. Yeah, so if I can get email addresses for people who are interested, next week, maybe the week after, we'll send a follow-up email with specific links. So the ACS does have a sequence of 6 videos for high school laboratory safety, designed for the high school laboratory safety audience related to emergency response. It's designed for students, for teachers to show the students and start discussions about specific laboratory safety issues. This is pretty high energy, high dynamic people. It's much better than the old 1991 version, which we disclaim routinely. The ACS safety website is simply acs.org/safety. And most of the information, pretty much all the ACS safety information is available there. If you would like specific questions addressed, we do have a Division of Chemical Health and Safety will can do email with you to help work through questions, figure out what are the key questions that need to be answered to help you come to a decision. We do want to hear feedback about this workshop. This is the first time Megan and I have done it. We're planning on doing it a couple times next year. So it would be great to get feedback from you, particularly about the Zoom aspect of it, because it's an interesting challenge to figure out how to make this happen in Zoom. And if you want us to review a procedure, if you decide to write a safety case or a risk assessment, you want us to review and comment on it, that's really, I think, the key point in when we say due diligence. We're saying that you're willing to have a peer review your work or your plans to say that, yes, this is reasonable under the conditions that you're planning on doing it. So with that, Megan, do you have any closing thoughts, or we can just go to open questions if you like?
I think that now would be a great time for us to entertain questions from our audience.
Okay.
One of the questions that I saw much further up was related to the many different ways in which we present hazards, specifically our diamond, for example, and our GHS symbols, and then warning and danger. And I was wondering if you could elaborate a little bit more on that.
So there's a long history, the 150-year history of chemical names that have evolved continuously through time. So one of the people I partner with a lot is the chemistry librarian at Cornell, and she is routinely frustrated by the fact that what was called benzene in 1920 is different from what we call benzene in 2020. There's a long history to how those names get assigned in the literature and in the trade. And then same thing happens with chemical hazards. So you may know that flammable means one thing in one place and inflammable means something else in other places, or the same thing in other places. It's very distracting. So the NFPA diamond, which somebody mentioned, the four-cornered diamond with the different colors, is built for about 600 chemicals. It has about 600 chemicals that are included in it. And there are 70 million, I think is the last number I heard, different chemicals in the world. So NFPA does not have the resources to go through and classify 70 million chemicals. And that's what the GHS is built to do. So what we see is that over time, just like the names of chemicals change, the names of the chemical hazards change. And GHS is the first scientific approach to naming hazards in a systematic way. And for that reason, I really appreciate the value it adds, even though there are confusing things about GHS. It adds a lot of value to understanding what's going on in terms of chemical hazards. Did you have anything more specific in mind than that, or just a general answer?
If that did not answer the question that the individual had, please let us know.
So maybe people were interested in the beginning in COVID. Our COVID strategy at Keene State. So Megan hasn't been to campus since spring break, I don't believe, because
I went today.
Oh, you went today. Okay. So I've been on campus ever since, because I was teaching. Actually, Megan was taking the course I was teaching in the spring, and since spring break, we shut down in spring break. We strictly relied on Zoom to close out spring break. All summer, we have been building a plan for campus as a whole, labs in particular, because our several research labs kept going over the summer. What our primary strategy is reducing occupancy. So Keene State has the most strictest occupancy limits of any campus in the system in New Hampshire. We decided that 38% of the fire code occupancy was what we would do in order to give us 6 feet in all directions for our students. Other campuses think that 3 feet is adequate, but we don't think that. So we've reduced most of our classroom capacity to about half. In the chemistry lab, I think you said 8, Megan, is what the plan is, which is a little bit more than half, I think. I think your previous.
We can have 18 students. Not
Okay.
18, 16 students, sorry. 16 students plus the instructor, and usually there's a lab technician milling around, so it is about half.
Yeah, so we're cutting our capacity in half. We are providing masks for everybody on campus, cloth masks, 3 cloth masks for everybody, every student, faculty member, and staff. And we have a supply of disposable paper masks as well. So what I call community protective equipment, masks, gloves are being supplied by campus across campus in general. So that's the second element. A third element, which we are just in the process of figuring out, is HEPA filters in classrooms. We have a collection of HEPA filters we'll be deploying to classrooms. I have not figured out the best strategy for doing that yet. I know I won't be putting in the laboratories because laboratories have so much ventilation to begin with. There's no way a HEPA filter can keep up with it in a laboratory setting. The problem we're facing when it comes to ventilation strategies for COVID is that we don't know where the sources are. We have to assume that anybody in the room could be a source of COVID and or of the coronavirus. And so if you have 8 people in the chemistry classroom, and we know actually in the back of Megan's background there is the chemistry classroom where we're talking about, and we have 5 hoods. So we know that all the air is moving in the direction of those hoods. So if there's a student who's infectious on the right side of that picture, and there's another student who's close to the fume hoods, the air from being expelled by the student will be moving in the direction of the fume hoods towards the potentially non-infected student. So I am still trying to figure out what the best way to manage ventilation is in that setting. Like every college campus, we have a wide variety of different buildings. We have buildings with ventilation systems, we have buildings without ventilation systems, we have half ventilation systems for some spaces. So it's going to take a classroom by classroom evaluation to figure out how to make the best use of the HEPA filters we have available to us. And that's a piece we're moving on. So, and then the final, the backstop for all of this is testing. So all students, all faculty, all staff will be tested before they come to campus. I was tested on Tuesday. I came back negative, so I'm feeling good about that. But obviously 2 weeks from now, that could change. So we have to have ongoing awareness of what the health status of the campus as a whole is in order to know whether the system that we're putting together is working. So that's sort of a quick synopsis of the strategy that Keene State's taken with regard to COVID. Does anybody have any questions about that? What is your primary concern in regards to chemical safety in high school labs? My primary concern are teachers who may be repurposed from another department to teach chemistry for this year. YouTube is a source of lots of bad ideas, and several of those bad ideas have led to bad situations in classrooms. That's my biggest concern. GHS stands for the Globally Harmonized System for Chemical Labeling and something. Globally Harmonized System is the way I think of it. Where are
We
you
have a
looking?
couple, sorry.
Go ahead.
I was going to say we had a couple of questions earlier in the chat that I've been trying to make sure that we're addressing as well. One of the questions was wondering if you are seeing things like near miss reports or level A responder hazmat be safe kind of analysis expected to be in high school.
No, I think the focus is more on planning than it is on incident response. So the interesting thing about that is that the response will be done by the fire department. The local fire department is the responders, and they're going to treat anything related to hazmat as a full-on hazmat event until proven otherwise. And so, but their focus is on controlling the hazmat event and then walking away. Once the event's under control, they don't have to clean it up. It's not their job to clean it up. It's the owners of the chemicals who are going to clean it up. So at Keene State, we've had probably 4 or 5 hazmat events since I've been here, over 5 years, and they stabilize the situation, and I'm the person that either cleans it up myself or hires Clean Harbors to clean it up. So I don't see that getting into high schools. It would actually be kind of nice to figure out how to get high school students aware of hazmat concepts, which are very different from chemistry concepts, particularly after the explosion in Beirut a couple of days ago. It's clearly a public safety issue that more people need some education about, given what, well, I don't know all the aspects of the Beirut situation, but I think that hazmat has gotten a lot of publicity over the last 6 months with the COVID. The idea of hazmat thrown around a lot and mixing around with COVID, but it doesn't, not in a very coherent way. Is there another question that you found?
I just wanted to give you 5-minute warning.
Okay, thank you.
Yep.
Please,
Not that I have.
Oh, electricity. Yeah, that's a good point. So I don't mention, we don't explicitly mention electricity in laboratory in the RAMP program. Electricity is, and it's not as bad as it used to be. 20 years ago when I was at UVM, a lot of people were building their own electrical instrumentation, and they leave bare conductors around. I'm hoping that doesn't happen too much in the high school setting too much. But I do know when I was in high school that the shops, students would be building their own electrical instrumentation, and I wouldn't be surprised if that kind of work is going on now. So electricity is something that's high profile. Where am I looking to get good COVID risk information? The COVID situation is changing very rapidly, both in terms of the scientific knowledge associated with it, plus the epidemiology and how much there is. I have a fair number of different sources that I track, and then I weigh those sources against the official advice from the government agencies, both at the federal and the state level, and try to sort of anticipate where they might be going. And that's how we came up with our system of community protective equipment, spacing in the labs, HEPA filters, and testing as our primary COVID control. But I don't think there's any one place you can go to right now to get going up-to-date COVID information.
So, yeah, so that's what I've been finding. I'm down here in Connecticut. The one community next to us, it was like 1 out of every 580 people passed on the last round.
Yeah.
And then when I look, I do a lot of relatively people would consider risky behaviors and diving and climbing. And when I look at the risks of I'm just doing my own calculations, which seems outrageous. And so you're doing the same thing I'm doing. You're reading a bunch of different sources and you're doing your own calculations to figure out your policy for your school.
Well, most of my technical experience is in ventilation. And so that's where I've been thinking about that. But it's not a situation where you can rely on any one of those levels that Megan talked about. It's a combination of all of them. And yeah, so it's at a practical level. So I get an email every day from OSHA reminding me about best practices related to COVID. And some of the statements are so broad as to be not useful. And so you have to sort of interpret that in the light of everything else you're seeing.
Thank you.
Thanks. So I will collect all the comments here. We'll save those into a file so that I can follow up with people who give me your email address. Drasa, is the files that I sent today, are they available on the website now, or should I send them again, or?
I think they are. Let me just double check this. Yes, I see like, I think it looks like 2 Word documents and 2 PDFs. Does that sound right?
That sounds right.
Okay. And also in that same folder is the link that I sent you guys that just has some of the discussion notes. And I copied everybody's email that posted it, and I put that in there as well. So you can have access to that.
Perfect. And if you can let the rest of the conference know that I'll be collecting emails from anybody who wants more information, that'd be great.
Okay. Do you want to only do it from people who ask? Because we could also send it out to everybody who's in the conference.
I could do it that way too. I just have to write it a little bit differently than what I had in mind. So yeah, it won't be till next week that I get to this. So
that's fine. Yeah, it seems like something like this would be a valuable resource for anybody who teaches chemistry. So if you'd be willing to put something together, we could send it out to the whole group.
And you've recorded this so that they'll be available to other people.
Yes. Yep.
Great. So my email is ralph.stewart, STUART, @keene.edu. And I think Megan's is pretty much the same, right? Megan.ferm@keene.edu. So feel free to give either of us an email if you have a question that follows up. We're both very interested in understanding best how we can support safer chemistry in the high schools, because we get your kids after you're done with them. So we'd like to have educated kids when they show up on campus. Thank you very much.
Thank you very much. We really appreciate your time.
Yep. Bye.
Bye.
Thank you all.
And just a reminder to everybody that starting in 1 more minute, we've got some closing remarks. And then later on this evening, we've got the optional coffee house happy hour and then a watch party later tonight. So I hope you can join us for some of those. All right, I'm gonna end the session. Ralph, or Megan, do you guys need anything before I end it?
Nope, we're all set.
Okay, great.
Thank you so much.
All right, bye everyone.
Bye.
Bye.